Okay. Okay. Now what we are going to do is, as I said yesterday, we are going to work with double integral over general region. The formula is really clear for each and one of you, I hope. The mechanics is really what matters. And we are going to use it because vector calculus, it is really based on lots of integration. So I want to develop that skill. Okay, the double integral over the general region, you break this region into small pieces and you have the height. So this is area element in each square and the height is block, and then the Riemann double sum is this one, and we have that integral. So the volume is going to be dA multiplied by dx, that is a of x of g of x. You are slicing all this, and it becomes actually double integral, or we call it iterated integral. So when we are dealing with double integral, we can have type 1 or type 2, just like single variable integral. So are we going to slice it in terms of y and then push it over here? Or are we going to slice it vertically and push it forward? That is what we have to integrate. So this one, what we are going to do is, if you are really having vertical stripe, the change is going to be in the y direction as you are moving this, and then integral from A to B, from here to here, and integral from y1 to y2, that is, and then dy dx, you are going to really integrate. Actually, we're supposed to change it, dx dy. So, and the second one is type 2, and then now a function of y, that what we are going to do is we are going to have horizontal stripe, and the thickness is dy, and then we are integrating from C to D, and you will put actually the right integral, the right limit minus the left limit is going to be the boundary, and that is h of y1, that is the lower, and h of y2, h of 2 of y is the upper one. All right, let us do this example. I want to compute the double integral of this function. Compute the double integral over the general region. Here, I want to draw the region. I want to set up your integral and then evaluate it, please. Okay, always what you have to do is really draw the region, the first square root of x and y cubed. And when we draw the region, we can really put it, because this is the intersection of two regions. The square root function is in the first quadrant, and the cubic function also will go through that. And let me put this is y is equal to x cubed, and this region is y is equal to square root of x. And now, by the way, for this we have two choices, and we can make it type 1 or type 2. So let me make it type 1, and then we'll do type 2 as well. And here, what is really changing is dx. I have, and the height is changing from the lower, which is square root of x, to the upper, which is the the upper square root of x and the lower x cubed. So what we have to do is write the region, set of ordered pairs, such that x is changing from where to where? From 0 to 1. And y is changing from x cubed to square root of x. And this is it. Then now, what we are going to do is, we have to really set up the integral based on this. This is really the important aspect. As long as you write this one, you will be fine. All right. Then now, what is really happening is the integral over the region R for xy minus x cubed. I'm sorry, my y cubed. Y cubed dA. Now, always the constant will be in the outside from 0 to 1, and the variable is inside from x cubed up to square root of x, and the integrand, which is for xy minus y cubed. And the internal variable of integration is y, so dy, and the external is dx. And we are good to go. Then after this, actually, the integration part will be very straightforward. Okay, well, let us do it. From 0 to 1, when we integrate this one, it will be 2x y squared, because 4x is really constant, and minus y to the 4th over 4, and this is evaluated from x cubed up to square root of x, and will be integrated with respect to x. Okay, when I put actually the square root, so I will have integral from 0 to 1, and this is going to be the square root of x squared is x times x is x squared, so I have 2x squared. And when I put actually the square root of x, so y to the 4th, so it will be simply x squared over 4. And from that, I'm going to subtract. Well, when I put x cubed here, it will be x to the 6th power and x to the 7th. So 2x to the 7th power. And when I put actually x cubed here to the 4th, that will be 12. And that's it. Then now let us really combine like terms. Okay, and x to the x squared I have, and here I have 2x to the fourth power. Let us really expand it. No, x squared, and here I have also x squared. So 8x squared minus actually 4x squared, that is 7x squared. All right, and then this really will remain the same, negative 2x to the 7th power, and negative over negative will make it positive, x squared over 4, x to the 12th power over 4. Then we integrate with this one with respect to x. So when we integrate this one with respect to x, actually 7 over 12 x cubed, and when we integrate this one 8, okay, and we have 2, that means x to the 8th power, and 8 divided by 2 is 4, and this is 13, and 13 times 4 is 52. And we evaluate this one from 0 to 1. Okay, this will give me actually 7 over 12 minus 1 over 4 and plus 1 over 52. Okay, so let us make this one 7 minus 3 over 12 plus 1 over 52. 7 over 3 is actually 4, 7 minus 3 is 4. 4 over 12 is 1/3. Okay, let us multiply. This is 52. And this one is 3. 3 times 2 is 6. 15, 156. So the answer is 155. I'm sorry, 55 over 156, and we're done. All right. Now, can we do it alternatively, guys? And that will be what? Well, let me draw the region. By the way, is this clear? I have done this all. As long as you set up the integration is really straightforward. All right. And now let us really do it the other way around. And remember, this is y is equal to square root of x, and this is y is equal to x cubed. And then instead of type 1, I'm going to make it type 2. And this y, the thickness is dy. And now this is changing from 0 up to 1. This is 1, and this is also 1. And now let us change this function. It is x is equal to y squared. And when you change this one, this will lead us also to x is equal to the cube root of y. Okay, once you have this, then what will be the region R? The set of ordered pair xy such that this time y is changing the constant from 0 to 1. And then x is changing the variable. What do you do? From the right, left. So the right function is the upper one, which is the cube root of y. And the left function is actually x, that is y squared. And this is it. Then now your integral over rectangular region, that function 4xy minus y cubed dA will be changed into integral from 0 to 1, integral from the y squared up to the cube root of y, and 4xy minus y cubed and dx dy. And you can really do this integral, and the end result is going to be the same. Do I have to repeat this one? I don't think so. You can handle it, yes? So we set up the integral. Shall I move on?
Sure.
To the next thing. Good. So this is really what we need to do. And now, if you understand this, the main thing is really setting up the domain is important, as I said. So as long as you set up the domain, you will be fine, or the region in this case, although I call it domain, because that is where we are going to really take the integral. So I want you quickly to do this. Draw the region and set up the limit of integration. As long as you set up the integrand, that is really easy. So please go ahead. Okay. So as you see, the y value and the x value are really changing. So let us see what is happening. Okay, let us see the first region is y is 2 and y1. Let us draw that. Y is equal to 2. Let me make this one 2 and this is 1. So I have this line. and I have this line. Okay, and the other one is x is changing between y and y cubed. Let us draw x is equal to y is equal to x is really a straight line, nothing like this. This line is x is equal to y, or y is equal to x. Okay, and x is equal to y cubed. That means what? Y is equal to is the cube root of x. So the cube root function, it will come through this and pass through the point 1, 1, because the cube root of 1 is gone, and then it will go somewhere. And obviously, these two functions has to intersect someplace. Okay, I have this line, x is equal to y cubed, or y is equal to the cube root of x. And then now we can really integrate. When you draw the region, it is really straight forward, and we can integrate it. All right, so this is a setup that we can really do it. Integral over the general region R e raised to x minus y, and now dA first, but I have to make a decision now. As you see here, x is changing. X is changing from this function to this one. That means it is type 2. This is dy, and y is changing from 1 to 2. So integral from 1 up to 2, integral from y up to y cubed e raised to x over y, and then dx and dy. Okay, I don't know how to integrate, guys, this one. That will be the integral, guys. I need your help. What technique shall I use? It is U substitution. Let U equals x over y. Du equals 1 over y dx. Then dx equals what? Y times du. So this is e raised to u, y times e raised to u, and the antiderivative of e raised to u is e raised to u. Therefore, based on this, actually, I can have the integral from 1 up to 2, and y, I have the antiderivative of the function is the function itself, e raised to xy, x over y, and this is evaluated from actually x is equal to y to x is equal to y cubed, and I'm going to integrate with respect to x then. Okay, so now let us evaluate it. Wherever x we have, we are going to put y. So I have in the first place y, and that is e raised to y cubed over y is y squared minus y, and actually y over y is 1 is a power of 1. Just I could write it e just to show you. And this is integral from 0 up to, I'm sorry, from 1 up to 2. Integrated with respect to y. No, nobody corrected me here when I put x. I already integrated with respect to x. Okay, well, then now what happened? The good thing is this integral is also simple. We can use u substitution. Let u is going to be y squared, and the du is going to be 2y dy. Therefore, dy is going to be 1 over actually 2 dy. Therefore, as a result, this integral becomes 1 over 2 e raised to y squared. And now this is I have e and I have y. So these two are not going to be really taking the product. Therefore, I have to do integration by part. Am I right, guys?
I believe so.
Huh?
I believe so.
No. You see, at least you are responding. Thank you very much. E the power of 1 is actually what? A number, e, 2 point something. It is irrational number. Okay? So there is no variable. It's not exponential function. We don't do actually integration by parts. Simply we integrate y because e is a constant. So I have e, and then the antiderivative of y is y squared over 2. That is what you have to do. The reason why once in a while I'm asking you is actually when you are quiet, I worry whether you are following me or not. And there are actually in my calculus one, when I call on their name, at least 2 kids, find them, they just turn on the computer and run away. All right.
Well, a lot of the time I don't speak because I'm writing through the problem myself, and
Yeah, that's fine. That's fine. Just I want to know whether you guys are really participating or paying attention or not. If it is in the classroom, I can read your face, I can see what you are doing and so on. But here, where I am, and actually, I don't want to talk to myself. I want to make sure that my students are really following me. Okay, that is the point I'm trying to make. Okay, once we have this, I mean we are settled, and then let us evaluate it. When it is 2, 2 square is 4, so we have 1/2 e to the 4th power. This is a number, guys. I don't want to get confused because it is raised to some number. Just like 2 to the 4th power, e to the 4th power is a number. Minus, when I put this one, actually, 1 squared is 1. Therefore, I am going to have yeah, 2 squared, 4. 4 over 2 is 2. So 2e. And then minus 1 over 2e, because when we put 1 square is 1. And this one, when you put 1, this is e 1/2 e. And these two are going to be cancelled, and minus 0 is the same. Therefore, you have 1/2 e to the 4th power minus 2 times e, and that is the integral. Okay, well, the problem is, can we make it type 1? That means vertical stripe. If we can do, what will be the shortcome? Yeah, we can do this also type 1. How? Well, the first place we have to really find the integral. I mean the region, this value, the intersection of this line and this line. Of course, it is 2. When it is really 2, what is really happening? That is what we have to focus on. All right, and then the lower limit is the cubic function, the upper limit is the linear function, and you are integrating it from here to here. But once you pass it through, what will happen? The lower limit is still the cubic function, but the upper is a constant function too. So you are going to do it twice. Other than that, there is no problem. Do you understand what I'm trying to say? Okay, good. So do please solve the same problem with alternative setup. Okay, understand? Change the order of integration. And that is your exercise, Tom. And you better get the same answer. All right, do you have any question for me before I go? Move on to the next problem. I'm not going anywhere. Okay, the other thing that if you remember, double integral can be actually used to evaluate what? Area. Compute the area of a two-dimensional region using double integration. Use, for example, the density function, which we will call it the integral f of x y equals 1. Since volume is what? Volume equals base area multiplied by height. So the area of the region R is what? The integral of 1 times dA. Because the density function f of x dA, so this 1 times dA is dA. Then the double integral is going to be integral from A to B, and the lower function g of x and the upper function g sub 2 and dy dx. So when you integrate dy, actually it will be y. And when you evaluate that, it is g sub 2 of x minus g sub of 1, which is what you learn in integral calculus of single variable. So it is the same. And you can do the same thing with actually type 2 regions. And this time you are going to integrate it from first with respect to y, h of 1, h sub 1 of y up to h sub 2 of y, dx dy. So the antiderivative of dx is x, then evaluate is h sub 2 y minus h sub 2 h sub 1 y and the dy. And that is actually what doesn't contradict what we learn in single variable calculus. Remember doing this, yes, guys? Double integral can be used actually to find area of a region. So compute the area of the region. Here is an example. Bounded by the curves y equals x plus 2 and y equals 4 minus x squared. always when you do actually double integral, you have to come up with the limit of integration. That means the region, in this case the domain, and that can be achieved actually by having a picture, and you'll have a clear cut of that. So draw the region. Okay, this is 4, y is equal to 4 minus x squared, and when y is 0, x is 2 and negative 2. Roughly, my parabola looks like this one. All right, and then the next one is the linear function. By the way, this is y equals 4 minus x squared. And then y is equal to x plus 2. The y-intercept is 2. And the x-intercept is negative 2. And then now we are going to really draw. Okay, I have y equals x plus 2. Okay, now you have to make a decision. Do you want to make it type 1 or type 2? Well, in the first place, whether we make it type 1 or type 2, before we make that decision, we have to really find this point. All right, if we make it type 2, it is from the line all the way up to this point. What happened? From the line up to the parabola. But here, from the parabola to the parabola, it can be done, but you have to be careful. So we have to outsmart the problem. Then if I were you, what do? I will pick actually type 1, like this. And this is a reminder for me, dx. And I'm stacking up toward this, moving in the x direction from the top to the bottom. Okay, well, this is really how we do it. So let us come up with the region R. The set of ordered pairs, x, y, such that, do you understand the argument I'm making, guys? Okay, if we make it horizontal choice, as I said, it will be 2 integral, and you have to convert the function, and it will be really a lot of work. Okay, well, to find the region, how is x is changing? I don't know what x is changing. Well, actually, mathematically, I can find it. This point is really 1. And I can say, actually, x is changing from negative 2 up to 1. And y is changing from the linear function, x plus 2, up to the quadratic function, 4 minus x squared. And that's it. By the way, someone will argue how you come up with this one if it is not really given. Well, what I am going to do is I have to equate these two lines. In other words, curves. Y equals y. That means the first y is 4 minus x squared has to be equal to with the second y, which is x plus 2. And then let us bring everything on one side because it is quadratic. That means x squared plus x minus 2. Because this form becomes negative 4 with 2 that's it. And as you see, this is factorable. X plus 2 and x minus 1 equals 0. Therefore, x is equal to negative 2, which is this, and x is equal to 1, which is this point. That is the choice you have. Then now, the area equals integral over the region dA. And this equals integral from negative 2 up to 1, integral from x plus 2 up to 4 minus x squared, and the internal is dy and the external is dx. And I'm sure you can finish up this work, and the answer is 9/2. But since I'm running out of time, I want to put something in your head, actually, the summary. Maybe your previous instructor mentioned this one, or maybe not. How do we determine or decide the actually order of integration? There are three possibilities. One is the integrand itself. For example, you have e raised to negative y squared dy dx. If you try to integrate this one with respect to y, no way, Jose, you can handle it. It's not elementary function. Therefore, without any choice, we have to reverse the order. The second, by looking at the region will dictate us, the one we have done already. Because instead of really having two integrals and converting the function, actually setting up the integral like this is really helping me to make it vertical choice. And the third alternative is when both the integrand and the region are actually influencing it. For example, if you see this one, y over x squared plus y squared. Well, if you try to integrate it with respect to x first, then this is going to be arctangent. And that might be giving us actually a problem. But if you integrate actually with respect to y first, you are going to use u substitution. Let u equals x squared plus y squared, and du is going to be 2y dy, and then you can really. And this limit of integration also will be affecting it. One, look, this region, you can make it vertical stripe. And if you want to make it horizontal stripe, you will be dictated here. Look, you have to have two integrals from the linear to the linear, from the constant to the linear. And both the region and the integrand are influencing it. So these are the three factors. And I will really do Monday these sets, so you can have a good picture, because when you are really working on line integral or surface integral for that matter better. I hope this helps and refresh your memory. Yeah.
Yes, thank you.
All right. Thank you, guys. Enjoy your weekend and make sure that you take the test, okay? Either today or tomorrow. Tomorrow is not your day. Do it today. I will send you the access code on your warm-up message, and or on your email. I don't know. Warm-up is better. And get that and start it. Put aside. Okay? Thank you. See you Monday.
All right. Thank you.
Yeah, yeah. Thank you.